my voice. I've been flying around a lot lately, and you pick up bugs in aircraft cabins, but I shall endeavour to continue throughout this talk. As this presentation revolves around the use of time-of-flight diffraction for production welding. It is also applicable in many ways to phased array, and utilising the code cases which are now in the boiler and pressure vessel code has now been embodied into the main body of the code, as Michael has been explaining earlier. My feedback is based on practical experiences. I refer to it all as code case TOFT. It applies to code case 2235, which is now a mandatory appendix, and also B313, code case 181. The acceptance criteria tend to be based on length and, well, the aspect ratio of a flaw. It could be just length, often limited to 4 times the material thickness, and the aspect ratio. And so aspect ratio being length and height of a given flaw. And my experience is that interpretation of time-of-flight diffraction tends to be simplified such that it becomes easy to procure, such that NDE vendors can easily train people up to recognize very simplistic flaw indications. And as Michael mentioned earlier, there is an interpretation guide in ASME 5, which has got some very clear-cut examples. As Michael just read out, I was a co-author of BS 7706, and I introduced images into the standard to help people to understand what time-of-flight diffraction is all about. And these are very clear-cut, simplistic defect types, and they're things like, I mean, in ASME 5, the surface breaking flaw is clearly a notch, and the lateral wave goes around the notch. The notch blocks the energy completely. In real life, you seldom, if ever, see this. I've been doing time-of-flight diffraction for 25 years or more, and I've maybe seen 2 or 3 indications that actually block the energy completely. You just don't get that. And I've seen situations where people are trained on notches, and they're trained to see a deviation of the lateral wave. And if they don't see that, they don't have a surface breaking flaw. And similarly, with a far surface breaking flaw, if you've got a wide open crack, it will block the energy going through it, and you will get a loss of backwall echo associated with the crack tip signal. But in real life, you seldom, if ever, see that. I've maybe seen it a handful of times. But people are trained that if you've got a far surface breaking flaw, you see the crack tip, you get a loss of backwall echo, it's surface breaking. You don't get that, it's not surface breaking flaw. Similarly, with buried planar flaws, you get phase reversal. You get phase reversals under idealistic situations, but you seldom see it in real life. But if people don't see that phase reversal, it isn't a planar flaw. And as a consequence of this, people tend to accept really poor quality welding and pass it off as being code compliant, and it really isn't. Also, the qualification requirements, I mean, the code cases, they define what is required in terms of qualification, and they say a minimum of 2 flaws. And there is a tendency in contracts, procurement contracts, just to move towards turnkey contracts where you let the fabricator decide how they're going to do things. And they will often go to the minimum requirements. Now, obviously, there are responsible fabricators, and there are those who will do whatever it takes to get below a certain price level. And if they see that the code allows you to use a minimum of 2 defects, then they will use 2 defects and no more. And in many cases, it's just not adequate. Also, the design considerations of structures are such that there is no special consideration given to weld properties. The material strength is regarded as being homogeneous, although the welds generally have lower toughness than the parent material. But the conservatism that's built into the design codes caters for these variations in material properties. But the design assumptions are that the material will have certain degree of strength. And that the design assumptions are that the welds are produced in accordance with good workmanship principles. So, you know, if a weld has a strength of a bar of chocolate, you know, it's just not fit for purpose. It's just not suited for its intended use. So these design considerations need to be taken into account. And if you have a situation where people are ignoring weld defects and producing welds that are riddled with defects, then that's not really what the designer had in mind, and that's not really what the end purchaser wants. And I would hope to think that it's not what the responsible fabricator would want to be producing, but it does happen. Could I just get some water, please? Let's take from the bottle. All right. Oh. Thank you. Excuse me. So the code cases and the mandatory appendices also allow the use of ECA-derived acceptance criteria, which allows flaws with a significant through-wall extent and also a significant length. And the question I'd like to raise is, why do we want to do that? Why do we want to go there? Is there a reason for going there? I think the reason for the code cases was to be able to use ultrasonic imaging technology instead of radiography. Was the original code case 2235. In the case of code case 181, the objective was to be able to use ECA-derived acceptance criteria, but that really opens the door for abuse. Now, I know a lot of people use the code cases responsibly, but there's an awful lot of people out there who aren't, who find a way to use the code cases to reduce the fabrication quality. So which is what I mean by the third bullet there, this can lead to a justification for poor fabrication, the use of ECA acceptance criteria. If you look at BS 7910, the fracture mechanics code, in the introduction it actually states in there, the use of an ECA can in no circumstances be viewed as an alternative to good workmanship. And I've seen many situations where a fabricator has realized that we can allow flaws up to 4 times the material thickness in length and in height, a height that equates to several passes. And they know it's hard to produce a flaw that high. So they can just relax all of the weld quality control and just produce poor quality welds and get away with it. And clearly the use of ECA is not intended to do that. It's wrong. I just mentioned this actually, with Toft and phased array, planar flaws are identified through amplitude of reflection with phased array, of course, but if it's not preferentially oriented specular reflector, you would look for continuous interlinked indications showing that you're walking up and down the face of a planar flaw. With Toft, ID connected flaws, you would tend to get a loss of back wall in a really extreme case. And again, for an OD connected case, in an extreme case, you would get lateral wave loss or deviation. And for buried planar flaws, you would look for phase reversals. But that is just really too simplistic an approach to the interpretation of UT imaging systems, whether it be time of flight diffraction or phased array. What I've experienced in real life is that a through-wall transverse crack can be acceptable in a situation where your acceptance criteria are based on length along the weld and through-wall height vertically through the weld. That means that a transverse crack has no length, no measurable length. So it's acceptable. And this is what people do. This is the way they interpret it. You know, it's in black and white. I've seen welds that are from top to bottom and end to end clustered overlapping indications have been deemed as acceptable because the operator couldn't see a phase reversal in there, couldn't see a deviation of the lateral wave, couldn't see a loss of back wall. It's acceptable. I don't think it should be. I think it's wrong. And also complex longitudinal, volumetric and transverse indications all overlapping really complex flaw clusters also become acceptable because they don't meet these aspect ratio criteria. But moving on to the contract requirements, when a fabricator enters into a contract with an end user, purchaser, they invariably sign up to concepts such as implementation of good and prudent practice, good workmanship. They agree to work within applicable codes and standards, and they also agree to work within quality assurance systems. And those quality assurance systems, they will define what a non-conformance actually is. There's a definition there. And in particular, what I'm interested in is what is defined as poor welding quality. And when a non-conformance is identified, there is then a process, the quality management system kicks in, and the process should trigger a root cause investigation, corrective action, and preventative action to overcome this. And I think this flow is quite important. And you can actually, by using NDE in a smart fashion, you can actually head these quality issues off and prevent them from occurring. Whereas I find that in many cases, people are using the codes and the code cases to hide behind the codes and code cases to conceal poor fabrication quality. Now, if these principles of good and prudent practice and good workmanship and applicable codes and standards are adhered to, and the code cases and the codes themselves, the base codes and their mandatory appendices are implemented correctly, then welding quality shouldn't really be an issue, or NDE quality shouldn't really be an issue. A problem is that with turnkey projects, the QA that's implemented is inadequate, and often QA contractors are too understaffed and too multidisciplined to have in-depth knowledge of all the areas that they're required to look into. And often it's a tick box thing. They will say, do you have a procedure? Yes, tick. Do the technicians have the copies of the procedures? Yes, tick. And that's the depth that it goes into. Is it based on ASME 5 Article 4? Yes. Is it AWS D1.1? And that's the length, that's the depth that it goes into. And people cut and paste the actual codes and standards into their procedures, and they never get looked at again. And then they just go and do their own thing in the field. So if people do apply codes and standards properly, then fabrication problems wouldn't be the problem that they often are. Excuse me. As I mentioned earlier, the objectives of ultrasonic imaging technology are either to substitute radiography or manual UT with advanced UT imaging technology, to avoid the radiation issues, the duration of RT, and also to improve detectability of planar flaws in the case of radiography, and reliability in the case of manual UT. But it's often used in practice to, not always, but in many cases, they can be used to circumvent QA and QC fundamentals and to circumvent principles of good workmanship and good and prudent practice in terms of fabrication quality and NDE. There is a way forward. One is competency assessments. In my experience, competencies ought to be addressed at a much deeper level than just somebody having a certificate of examination. Having an ASNT level 2 certificate is not enough. Somebody can go on a 2-week training course and come away with a certificate and makes them competent. I think it should go a lot deeper than that. The qualification aspects of code cases should be used to demonstrate that the personnel are competent to implement the procedures to detect, evaluate, and sentence the types of flaw of concern. It ought to be, in my view, a more detailed exercise than just show that you can find 2 EDM notches. And also, with time-of-flight diffraction, and also this applies to phased array, they can be, if implemented properly, very, very sensitive techniques. This does put off a lot of fabricators when they see that you can find small flaws. many fabricators don't want to know. Until they start to learn, the more enlightened ones realize that the fact that you find a small flaw doesn't mean that you reject the small flaw. And you can use that high sensitivity technique as a quality control level. And if you use that as a quality control feedback to show that you're introducing systematic flaws, then that tells you something's going wrong with your welding quality control. You can feed that back, correct it, and prevent it from going any further out of control. So it can be used as a very effective quality control process. And we've seen this with automated welding processes, with fisheye formation, lack of interrun fusion that with other techniques is not picked up, but can, if left unchecked, it can start creeping up the sidewall and end up with lack of sidewall fusion, copper deposition through timing issues to do with the arcing. There are many, many different factors associated with welding that you can pick up with a highly sensitive technique and feed it back to the welding station and get it right so you don't introduce defects. And then the second level is good workmanship acceptance criteria. Why would we really want to move away from that and use ECA-derived acceptance criteria? Why do we want to allow planar flaws that are multi-pass in height through the weld thickness? What's the reasoning behind that? I mean, ECAs are really sort of developed for use in service where you've got a flaw that is difficult to repair, or in very hostile environment that's expensive to repair, and you use the ECA to determine how long you can leave that flaw in situ, or if you can live with it to the end of life of the plant. Or in fabrication situations, I've seen cases where, due to project timelines and floating a structure out on a vessel that's got to go out on a particular tide, and you don't have time to effect a repair, you might want to make a case on a one-off basis. But to use ECAs to justify leaving in major planar flaws and long indications, I'd question why on earth we would want to do that. Good workmanship acceptance criteria were originally developed to pick up on what a competent welder is likely to produce in terms of weld quality. If you get lack of sidewall fusion, if you get cracks, planar flaws essentially, then that is an indication that the welding procedure has been incorrectly applied. And the correct answer is not find a way to accept them. The correct approach is, if the weld procedure has been incorrectly applied, then apply it correctly. That's where the error lies. So I don't really see the need in fabrication for creating a case to accept large planar flaws. They should be headed off before they occur, rather than create a case to leave them there. And especially if you use this quality control concept and start to pick up systematic defects. In fact, prior to the fabrication, if you use these techniques during the weld procedure qualifications, then you get your welding techniques right before you even start welding. And then it's a case of just controlling them and implementing them properly. If you do all that, NDE shouldn't really be necessary, in theory. So, excuse me. The first stage of quality control, just to go into a bit more detail, is where reporting criteria are established to trigger when welding parameters go out of control. And that can then lead to a reporting feedback, which could be a form of statistical process control or just individual feedback. Root cause investigations, this is in accordance with the fabricator's quality management system. The root cause investigation, whenever these indications are detected, would determine the cause of the flaw. The corrective action would be, if necessary, which is why I put it in question marks, because at this stage we're looking at small flaws, and they may be acceptable flaws, so it may not be necessary to correct them. It may be just that you've seen them occurring, then the corrective action is really the preventative action, which is to prevent them from occurring in future and going out of control, but you may not need to repair them. Once the the trigger levels of the quality control have been identified, then the qualification should really be based on flaws that exceed those trigger levels. That's what you should really demonstrate you can find, rather than qualify on something that is borderline acceptable according to an ECA, which is a much, much bigger flaw. Good workmanship acceptance criteria, there are different approaches to it. The AWS D1.1 is a very thorough approach. It involves using a single angle for each weld zone, working at very high sensitivity with investigation of potential planar flaws, and then ultimately acceptance is based on the reflectivity of a flaw. We have to optimize your technique once you've found something that is potentially planar to ensure that your beam is perpendicular. It's a very well thought through process, not one that's widely understood, I don't think, outside of the US. ASME Article 5 is similar with European codes and standards, uses multi-angle beams passed through all of the weld from both directions and investigate anything that exceeds 20% of DAC for planar characteristics. Either of these two techniques can be used for acceptance. Time-of-flight diffraction is very good for detection. It detects flaws of various different orientations. It does have some weak areas. Phased array also has its strengths. But once an indication has been detected, they should really be assessed using one of these two techniques, either the AWS approach or the ASME Article 5. I don't think that you can beat the manual dexterity and the optimization of a signal that you get. When you're doing phased array and you're doing a linear array, you've got a single pass. You know, is your coupling ideal? Is your probe position or ideal to idealize to pick up the maximum response? Good workmanship acceptance criteria tend to be based on the reflectivity of flaws, the amplitude reflection. It's vitally important that the probe is in the right position and that you're optimized on that position, that indication, and that your coupling conditions are optimized. Excuse me. And implementation of these techniques require control. Another thing that I've experienced a lot is that with these automated and semi-automated inspection systems, the industry is losing manual skills of manual UT. There aren't that many UT technicians out there who are capable of characterizing flaws properly and assessing them against the code. And competencies are generally poor, and the feedback that I get from my work and from talking to other people and attending other conferences is that competencies are generally poor and are declining. So there is an industry need for improvement there. In terms of a project, a way forward is to, at the start of the project, agree on the objectives. Usually, or often at the start of a project, the contract documents are signed and you just get on with it, and people are left to their own devices, especially in a turnkey contract. What should be agreed are personnel competencies, the acceptance criteria that are going to be used, and the procedure qualification. As I mentioned earlier, the code case says minimum 2 flaws, you get 2 flaws, full stop, that's it. Does that really achieve what the end user wants? I would suggest that in many cases, if they really looked into it in detail, the end users would say no. In terms of weld procedure qualification, I am an advocate of using realistic flaws. I don't like using drilled holes and notches if you are proving a technique. Often you don't need a code case. If you're going to use good workmanship acceptance criteria, then this is a process that has been in use since the 1980s, is that you can produce samples or mock-ups that contain borderline acceptable flaws throughout the weld volume, near surface, far surface, mid-wall, various fusion faces and so on, various weld types, and then prove that you can find them. And with a technique like a high gain phased array technique or a Toft technique, if you can demonstrate you can find all those flaws, then you can use that as a screening tool and then go in with manual UT and assess against good workmanship acceptance criteria. And a lot of people object to producing these extra test pieces. And I don't really see why there should be such an objection when it's accepted that as part of every project, welded test pieces are produced to qualify the welders and to qualify the weld procedure. Why should we not at the same time produce samples with flaws as per API RP2X with welded shims on the fusion faces? Why should we not produce mock-ups like that at the same time? It's not a big deal. But people tend to run away from it as adding a huge amount of cost to the project. And if you do produce samples like that, then you can prove your detection capabilities, you can prove your characterization, you can prove your personnel competencies, and then it's a case of managing the implementation. And I would make a call for, on projects, there should be a better understanding of NDE by the QA organizations that monitor quality on behalf of the end users. So the end result is, if this approach is adopted of using this dual level reporting, proper qualification, a properly thought through acceptance process, that the product would be manufactured in accordance with the contractual terms and it would meet the customer's end expectations. And the manufacturer maintains product quality and reputation. We do work with some manufacturers who embrace these kind of concepts and they want to stand out from the rest of the crowd and they want to develop good quality product. And also repairs and associated fabrication delays and massive disputes can be eliminated altogether and everyone ends up happy. Just by thinking the whole thing through and deciding what do we want from NDE, what do we want from weld quality. We can head all these problems off. So that's the end result. That's the end of my talk. If anybody.
Thank you very much, John.
Thank you.